Hello students, this is part 3 of the gas laws lecture. This one's going to be really short because I'm really only covering pretty much just one subject, and that is mixtures of gases and partial pressures. And this video will help you to do one of the assigned homework problems for the homework 2 assignment. Obviously, we're changing the due date on that homework 2 assignment. I will put an announcement on that for Blackboard. So I think it's already past due or something. I don't know. I'll write the due date on it there, and I'll figure out a way for you to submit it to me. Anyhow, this will help you do the homework problem from chapter 4 that you're going to be submitting for the 8 points. Okay, so let's just get into it. So this video is about mixtures of gases. And remembering that a mixture was a topic we learned in chapter 1 or 2. Mixture is just something that contains more than one type of element or compound in it. And what we'll start out by saying is that most gas samples are actually not pure substances, meaning that it's pretty hard to get a gas sample that's all one type of element, either one type of element or one type of molecule, because gases always mix with each other. So anytime they're exposed to other gases, they're going to combine. So it's actually kind of hard to get a pure substance of a gas. So most gas samples are not pure substances, but mixtures, which essentially just means it contains greater than one type of gas. And that's kind of the most common situation. So as an example, let's think about, because this will help us understand partial pressures. As an example, let's talk about what we call air. Air is obviously a real thing. It's not synonymous with the word gas. Air is talking about the things, in the atmosphere, that what we can breathe in and breathe out. So that's air. And I do want you to know that air is a gas mixture. This is in your reading, but I'll put it here on the board. It actually has and it's got lots of gases in it. It's got pollutants and all this other stuff, but it's got 4 main gases in it, and I want you to know what they are. Air is actually mostly nitrogen gas, N2. I think I don't have these numbers memorized, but I'll just peek at it. It's about 78%. So about 78% of all the air that you're breathing are nitrogen molecules. The second most prominent gas in air is oxygen. That's good because we need it to survive. Oxygen is about 21%. Thirdly is argon. And argon is about 1%. And then carbon dioxide, which of course we are breathing out and the plants are breathing in, is about 0.04%. So these are the 4 main components of air. I'd like you to know that. But it actually will also help us understand the concept of partial pressure. So staying on air for a minute, let's pretend that we have a container full of air. And so I don't know, I could use this cup right here and put a top on it, and now I have a container full of air. So let's put a top on it so none of our gas particles can escape. And let's just kind of try to diagram air. So the most common component in air is nitrogen. So just for the sake of this diagram, let me draw 4 nitrogen molecules. Since he's the most prominent component or the most common component. Oxygen is the second most. Let me draw 3 oxygen molecules. Obviously, this is not to scale, but just trying to make the point that you have less oxygen than nitrogen. Thirdly is argon. Let me draw 2 argon atoms. Argon is a noble gas. It's not a molecule. It's an atom. And CO2 is the 4th prominent, and since he's the 4th most common component in air, we'll only draw 1 molecule for him. So I have kind of a diagram of air here. So obviously, once again, these are all very far apart from each other. Most of the air is empty space, and remembering that the molecules are in constant motion. Sometimes they will be hitting each other. Okay, so that they'll hit each other, and that's fine. But They will also be hitting the sides of the container. And whenever they hit the sides of the container, they create pressure. All right, so all of these gases are going to be hitting the sides of the container. Let me get a little bit of space over here now to introduce this next concept here. And this little diagram will help us explain it here. So what we have is I guess for us, we've learned the 3 simple gas laws. We learned ideal gas law. So this is our 5th gas law. And this law is called Dalton's law of partial pressures. So Dalton's law of partial pressures. And partial pressures are basically the pressures of one type of gas in a gas mixture. That's what a partial pressure is. So essentially, what I could say is that because all of these gases are kind of doing their own thing, they're all just bouncing off the sides of the container, you can actually kind of talk about the pressure that is exerted by nitrogen on the sides of the container. And then you could talk about the pressure that is exerted by oxygen on the sides of the container, the pressure that is exerted by argon, and the pressure that is exerted by CO2. You can kind of individually pinpoint the type of gas and think about what was his contribution to the overall pressure. So Dalton's law of partial pressure states this: the total pressure, it's P total, of a gas sample. So this is the total pressure of a gas sample. So if I'm using this container, if I was to think about the total pressure, it would equal the sum of all the partial pressures of each component. So a lot of times people will just say PA plus PB, etc., until you finish out the types of gases. But for me, since I'm talking about air, let me go ahead and talk about it like this. The total pressure is going to equal the partial pressure due to nitrogen, so to nitrogen's collisions, plus the pressure due to oxygen's collisions, plus the pressure due to argon's collisions, plus the pressure due to CO2's collisions with the sides of the container. So this is how you would write Dalton's law of partial pressures for this air sample. And the way that you verbalize this is you would call this the partial pressure of oxygen. And that's a good way to say that. If you have a specific component, you would call this a partial pressure of oxygen. So it's kind of just like the sum is equal to, or the total is equal to sum of all the parts. They're all hitting the container, and the sum total of all the forces will end up being the total pressure. So it's kind of like a really common sense type of law. Okay, so now let's think about this for a minute here. Of all of these partial pressures, what one do you think would be the largest? Which partial pressure would be the largest, the most force, per unit area? And hopefully you can see that nitrogen is going to have the largest partial pressure because he's the one who's going to have the most collisions, because he's the one with the most molecules, the most particles. He's the one that was the majority of the gas. Whereas which one would be the smallest partial pressure? It would be CO2, because CO2 only has, in my diagram, one particle, because he represented the least amount of gases. So essentially, what we're saying is here is that the more molecules you have, the higher your N value, the higher your partial pressure of that component. The partial pressure is going to be due to the number of molecules specifically. So you can kind of relate that concept just conceptually. Now, let me go ahead and do a practice question, and this is where this video will finish up here. And this, I'm going to not use my air sample, but I'm going to use just a practice question. So let's go ahead and state this here. A 20.0 liter mixture of 3 gases, O2, helium, and neon, has a total pressure of, let's see here, 0.875 atmospheres, at 298 Kelvin. I'm just going to write it like this, but the wording here on my notes is, if the partial pressure of helium, so I'm just going to write it like this, that's how we state partial pressure of helium, is 0.450 atmospheres, and the partial pressure of neon is 0.147 atmospheres. What mass of oxygen is present in the sample? So this is a question that you would want to be prepared to answer, both for the homework but also for the exam. Okay, so what are we being asked in this question? Step back and just reread it. What is the answer going to be? What kind of unit will be in the answer? What are we looking for? So you can see we are solving for the mass of O2, which is grams. In chemistry, anytime you need grams, and hopefully I've trained you well enough to know that if you can just get a different unit, getting grams is just so easy through molar mass. The unit that we could, if we can figure out a way to get moles of O2, we can figure out grams of O2. So hopefully you can frame your mind like that. If we can just figure out moles, then we can get grams. So that will be the first thing we want to notice. Second thing we want to notice is this. In the question, I'm giving a total pressure of 0.875 and two of the partial pressures, heliums and neons. What I would do is I would write Dalton's law of partial pressure. The total pressure is going to equal, in this sample, the pressures of all of the components, the partial pressures of all the components added together. And then I would just solve for the partial pressure of O2, which is the one thing that I don't know. So the total pressure is 0.875 atmospheres. I'm solving for the partial pressure of O2, and that would equal whatever helium was added to whatever neon was and so you would add these two together, get that sum, and then you would subtract that from both sides so that you could get the partial pressure of O2. And I misplaced my calculator, but it's okay because I have the number written down here. So the partial pressure of O2 would end up being 0.278 atmospheres. So hopefully you can get that. But that would be the partial pressure of O2. That would be the number that would have to fit in here so that they all equal that. So that's the partial pressure of O2 now, but that is good, but that's not the answer because the answer is looking for the mass of O2. The key thing here is that whenever you have a partial pressure of like one component, so you're zeroing in on just this one component and think about what pressure is he exerting on the sides of the container. You can write, I would just call it like an individualized PV equals nRT for just that component. Let me get a little bit of space here. Let me keep that there. So once you get somebody's partial pressure, you can write his very own PV equals nRT. His personalized PV equals nRT. As long as you use his partial pressure here, you will be solving for his number of moles right there. And that's what the individual PV equals nRT. Do you remember earlier I said as the number of moles increases, the pressure is going to increase? Like that's why nitrogen's partial pressure was greater because he was the one who had more particles. This is that same relationship being reflected. If you have a higher partial pressure, it's because you have more moles. But anyhow, you would just write your individualized PV equals nRT, solve for the number of moles, and then we're one step away from getting grams. So let's go ahead and do this. At this stage, let me just go ahead and rearrange for n of number of moles of O2 since that's really what I want. So I'm going to divide both sides by RT. Now I've got a nice equation. Let me just clean it up a little bit here. The number of moles of O2 is going to equal partial pressure of O2, which is 0.278 atmospheres, times the volume, should be in the question, 20 liters. On occasion, I've seen students try to figure out like the percentage of the partial pressures and try to apply that to volume. Understand that all the components will fill up the 20 liters. Every single one of them will spread out across that 20-liter volume. So you don't divvy up the volume. You use the total volume because for all those gases, they are occupying 20 liters. And then we're going to divide by R, which is 0.08206 liter times atmospheres over mole times Kelvin. And then the temperature in Kelvin, 298 Kelvin. Now look at your units, they're going to cancel nicely. Kelvin's going to be gone. Atmospheres is going to be gone right there. Liters is going to be gone. And what you're going to end up is with the mole unit, but in the denominator of a denominator. If you look at that, it's in the denominator of a denominator, and that actually bumps up to the top floor. So that is going to be your surviving unit, like not in a denominator anymore. Mathematically, it will bump up to the top floor. Now, be very careful when you enter this into your calculator. You're going to need to use, how I would do it is I would just do 0.278 times 20, enter, and then divide by, and we'll say answer divide by. Here, you want to make sure this entire thing goes in parentheses, this whole thing. If you don't, you're going to tell your calculator to divide by him, but times by him. That's not really what you want. You want to divide by the product of these two. So once you get 0.278 times 20 and press enter, then press divided by parentheses, 0.08206 times 298, close parentheses. That's the right way to enter that. And you will get, for a number of moles, you will get 0.227 moles of O2. And then you're just a short step away from getting grams. Hopefully you know that you would just use the molar mass. And the molar mass of O2, be careful, it's not just 16. There's 2 oxygens, so it's 32 grams per mole. And I will use my calculator on my thing. It's just in the other room, but I forgot to bring it in. Where are you? Oh, it's not letting me do it. Hold on. You go ahead and do it. I'll be right back. Okay, 0.227 times 32. There we go. 7.26 grams. And that is the answer. Okay, that's it for partial pressures. There is more that the textbook covers, but that's all that I feel us needing to cover for this chapter. So be prepared to do something like this on the test. Also on the homework, you'll see you have a nice practice for that. All right, one more video is coming, which I've already made about kinetic molecular theory. Thank you. Bye.